So other leakage currents we have already seen in the previous clips. The subthreshold conduction current or the subthreshold current is nothing but as an estimate is given by I equal to IDO into W by L into exponential function of minus VGS minus VT upon eta times VTH. Now the ideal value of IDO is 10 raised to minus 9 amperes. Let's assume the same value of capacitor as 50 femtofarad. Voltage change as 1 volt. We'll assume VGS is equal to 0 because this is the current which flows when my VGS is less than VT. This value depends on the value of the capacitance. This is nothing but KT by Q, which is 26 millivolts. Let's assume W by L as 1, and this is nothing but my threshold voltage. So if you try to simplify all this, I'll presume this current comes out to be as an approximation 10 raised to minus 9. So let's put this in the whole time equation again. So this is nothing but C out upon IL into V1 minus Vx. V1 minus Vx is the same, C out is the same, only IL changes. So this is nothing but 15 to 10 raised to minus 15 upon 10 raised to minus 9 into 1. When that's the case, you get your whole time reduced to 50 microseconds. So you understand that you will need a minimum frequency for your circuit to operate. I'll explain this term, what do you mean by minimum frequency, very shortly in the further clips. If your circuit does not operate at that frequency, you will tend to lose out on your value due to a problem called charge leakage. For the time being, what you need to understand from this clip is how is a high value getting degraded to a lower value just because of the leakage currents which are present in the circuit when the transistors are off. And hence, when this charge leaks, this will be a very common phenomena in DRAM circuits, which we'll see again in the further clips. You will need refresh mechanisms. Before we go ahead, let's complete the final formality. There are other leakage currents present also due to the physical structure and the materials used. And this leakage value can range somewhere around 10 raised to minus 7 amperes. So if I do the same substitutions with C out same, V1 minus Vx same, and IL is equal to 10 raised to minus 7, then what I get is nothing but 0.5 microseconds, which is again very less whole time. Ideally, what's happening here is, if we see, this is just an approximation. In reality, leakage current is a function of my voltage. So is my C out, which is also a function of voltage. Here we have seen an approximation of how we understand the leakage current, but in real time, my leakage current is a function of voltage and so is my C out. So this is how it's going to be technically. C out, which is a function of voltage, upon IL, which is a function of voltage, into dV, which is equal to T. If you simulate this in real time, what you will get is that your voltage does not decrease linearly, but your voltage would decrease somewhat in this fashion, where your initial voltage was V1, say this was your voltage Vx, and this was your whole time TH. So it's not a linear decay. So in summary, what we learned in this clip is, we learned the concept of charge leakage. We saw a C2MOS circuit. We saw a condition where both my NMOS and PMOS transistors which were connected to the output were off because of clock. At that point of time, we saw the PN junction diode reverse currents flowing because the bulk were connected to VDD or ground. And at that point of time, due to leakage currents, we saw that how if we assume the initial voltage to be V1, how did we start deteriorating, or how did we start losing out on that value with some equations. And then we further went ahead and saw some other leakage currents which reduced the whole time further, and we understood that we have to have a minimum frequency of operation for our circuit, and in order to not lose the value, we should also have refresh mechanisms in case of dynamic circuits. So minimum frequency and refresh mechanism we'll be seeing in the further clips. Hope you have followed this. Stay tuned. Thank you very much and take care.